we are here last time, okay? Yeah, we are here. But I need to explain something here. Yeah, because here, the derivative, C constant, positive, negative. Last time I explained increasing, decreasing. Yeah. So before we start here, I want to explain this property a little bit. Yeah. All right. So here I use this blank slide to explain. Okay. Yeah. All right. All right. Change my pen color. Yeah. So I want to. Yeah. So actually, you learn it in your calculus class, but here I just, review a little bit. Yeah. Because for this class, understand the meaning, geometric meaning is very important. Yeah. So here, we want to understand the geometric meaning of derivatives. Yeah. So understand geometric meaning of derivatives. Okay? Yeah. So original function, f function. Okay? F function, yeah. Here, let's use the same notation. Okay? So y of t, right? So our function. Y of t, t is variable, y function. Okay? And we want to understand its derivatives, y prime of t. What's the meaning of y prime of the t? When we look at the graph. Yeah. So let me draw the graph. Yeah. So here, yeah. In our first example, we use t. Yeah. All right. So here, I may like to, consider the general case x as the variable. All right. Yeah. Okay. So x-axis, y-axis. Yeah. First, we need to draw the graph y of x. We need to draw the graph. Well, suppose we have a graph like that. Yeah. All right. Because here we need to look at the meaning of the derivative. Yeah. We know, given a function, we cannot say its derivative always exists everywhere, right? We cannot say that. Okay? Only when this function is differentiable, then its derivative exists, right? So differentiable. Okay? Yeah. So only when this function is differentiable. Differentiable, right? Yeah. Its derivative exists. All right? Yeah. But when a function is differentiable, yeah, so visually, yeah, so what we look at the curve, visually it is smooth. So differentiable here. We look at it, it's smooth. Okay? Yeah. So you see, when you see the curve very smooth, oh, yeah, it tells you it's differentiable. Yeah. But yeah, here I draw another special example. If a curve is not smooth, for example, Okay, here. So at this point, it's not smooth. Change sharply. Okay, yeah. So change sharply. Not smooth. Yeah. And it means its derivative does not exist here. Okay. Its derivative does not exist. Yeah. Because derivative is closely related to tangent line. At this point, no tangent line. Okay. So there is no tangent line. Okay. No tangent line. No tangent line means no derivative. Okay? Yeah. So the geometric meaning of the derivative is related to the tangent line. Yeah. So this curve, visually we can see it's very smooth. So you can see there is a tangent line everywhere, right? Every point on the curve, you can draw a tangent line. Okay? Yeah. Here, let's assume we look at this point. So we draw a tangent line here. The tangent line. Okay? Yeah. Tangent line. All right. So then, the slope concept. Yeah. When we have a straight line, we have that slope concept. Yeah. Then, the geometric meaning of the derivative. Yeah. Here, I want to give a special point that let's call x0 point. Yeah. X0 point. We fix this particular point, x0. Okay? All right. Now, we want to consider derivative of this function at x0. What's the meaning of that? What's the meaning? All right? Yeah, because this tangent line, you can draw tangent line. This tangent line, there should be an angle, right? Yeah, so this is the horizontal line. Okay? Horizontal line. Horizontal line. And there is an angle between the tangent line and the horizontal angle. Yeah. We use theta. Okay? Theta. So the derivative equals tangent of that theta. Okay? Tangent of that theta. That's a geometric meaning. Okay? All right. Now we can use this understanding to understand the property. Okay? Yeah. The property is when the derivative is positive. Okay. When y prime is positive. Yeah. What do you mean? Okay? Yeah, because based on the here, how about let me use the theta 0. Okay? So 0. The subscript 0 theta corresponds to the subscript of x. Yeah. Theta 0 corresponds to x0. Okay? All right. This y prime of x0 greater than that means tangent theta 0 is positive, right? Yeah. Tangent theta is positive. Do you know in what range? What range? Here the range you only consider theta between 0 and 100 degree. Okay. So here because we only consider theta in this range between 0 and 180 degree. Okay. 180 degrees, sometimes we use the radian pi, right? Yeah. So here I just review the basic knowledge, okay? Yeah, radian, yeah. So 100 degree, if we use the radian measure, it's pi, okay? Yeah. Yeah. So here, in this range, theta between 0 and 180 degree, what's the specific range for theta 0 to guarantee tangent of theta 0 is positive. In what range tangent theta is positive?
0 to 90?
Yes, between 0 and 90. Between 0 and 90. Okay? All right. So the range here, the conclusion, the range must be between 0 and 90 degree. Yeah. Exclusive, not include 90. Okay? Yeah, because at 90 degree, tangent theta is not defined. Does not exist. Tangent 90 degree, it does not exist. So we cannot include 90 degree. It does not exist. Or you can say infinity. Okay. But it's not a number. It's not a number. 90 degree. Yeah. So, all right. Then similarly, when the derivative is negative, that means tangent theta 0 is negative. Then the range for the theta 0, the other half, right? The complementary part. Yeah. So that is the theta 0 is between 90 degree and 180 degree. Okay? Yeah. So what's that? Yeah. Because that is the case. Yeah. That is the case. Yeah. So here. Look at this point. Okay? So if you draw a tangent line, it's like that. Okay? Like that. Yeah. If I enlarge, so here, so the tangent line. Okay? Horizontal line. So this is the theta. Theta 1. Let me use not 0. Theta 1. Okay? That's the theta 1. This theta 1 is between 90 degree, theta 1, and 100 degree. Right? Yeah. So that's the geometric meaning. Then, if the tangent line is like that, then you can see the function is decreasing, right? Going down. Yeah. Because when you move along the positive direction of x, yeah. So you do not move from the negative direction of x. You move along the positive direction of x. The y value going down. Okay? So that's why it's decreasing. Yeah. But if the derivative is positive, when you move along the positive direction of x, y value is going up. Okay? The trend is going up. Yeah. So it's increasing. Yeah. So that's the basic knowledge. Right? Yeah. So I spent a lot of time here to explain. Yeah. So we can review a little bit. Yeah. Because for this class, we need a lot of basic knowledge. Yeah. A lot of basic knowledge. Algebra, geometry, trigonometry, analytic geometry, So a lot of knowledge. Calculus, yeah. Quite a lot. Yeah. All right. Yeah. So with this understanding, so next we can continue our solution part. Yeah. So let me. I should make it a larger. Yeah, because we need a full screen. We need a full screen view. Yeah. All right. Now, so yeah, here, let me quickly get to the place. Yeah, we are here last time, right? Yeah. So let's continue our story, the solution. Yeah. Now we try to solve this differential equation. Yeah. The C constant not equal to 0, so there are two cases. C is positive value sometimes, and because here, remember y is the amount of the substance, right? Yeah, amount of the substance. So Y is a positive value. Amount of substance, number of grams. So positive C times positive Y value. That means the derivative is positive. So Y, that means Y function is increasing. Okay? Then the other direction, C less than 0, Y decreasing, decays. Yeah. Yeah. So the decay model, we consider negative C. When we have negative C, so that's the model, that's the differential function representation for the decay model for negative C. For positive C, it's not a decay, but sometimes people consider generalized. Yeah. Because sometimes, yeah, because they have the same form. When C positive, negative, although the value different, but the form look the same, right? Form look the same, so then sometimes people call it generalized. Yeah. Okay, decay model. So for the positive C, we can call it generalized decay model. Okay? Yeah. Things like that. Okay? All right. At the beginning, we have no idea. Now, I try to describe the whole process of problem solving, yeah, because I want you to learn the thinking. Okay? Yeah. Not just to memorize the formulas. Yeah. So you need to, learn how to solve the problems by yourselves. Okay? Yeah. Based on your thinking. Yeah. All right. So at the beginning, we have no idea. Yeah. Because our toolbox is empty, right? We do not have existing tools, problem-solving tools at this point. It's, pretty empty. Yeah. Yeah. All right. So that means there is no existing tool we can use. That we need to use our background knowledge to solve. We have some background knowledge, right? Yeah. If you have no background knowledge, then it's hard. You cannot solve. Okay? So you have to have, adequate background knowledge. Yeah. So let's continue. Yeah. Golden rule. This golden rule means the problem-solving golden rule. Yeah. So our textbook, says that. The golden rule. Yeah. So what's that golden rule? If you cannot solve your problem, try to solve a simpler one. Yeah, that's the so-called golden rule. Yeah, describe it in the textbook. It looks so simple. Yeah, but why the author calls it golden rule? Although it's simple, but very useful, very effective. In many situations, you can use this simple golden rule to solve quite some problems. Here, that's one special situation. Yeah. All right. And this golden rule, yeah, on textbook page 19, step 2. You can find it. Okay? I'll give you the reference, yeah, on the textbook. Okay. Page 19, step 2. Yeah. And it also appears several other places. Okay? Yeah. This golden rule. Yeah, very simple. So you can see it's common sense, right? Yeah. So although it's like common sense, but it's golden rule. Yeah. All right. But there is because this strategy is very important in problem solving. Okay. Yeah. So when people study the problem solving, yeah, look at the many strategies. So this is one of the strategies in problem solving. Yeah. Yeah. So regarding the problem solving, there is a famous educator called Polya, Hungarian mathematician. Yeah. So very famous. Yeah. So He wrote a book. He wrote a book in 1945, that early. Yeah. He was a Stanford professor. Yeah. 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 He's a well-known mathematician and educator. Okay? All right. So he wrote a book called this name, How to Solve It. The book title, How to Solve It. Okay? Yeah. Not very thick, yeah. But its impact is big. Okay? In that small book, he discussed all the problem-solving strategies, procedures, step 1, 2, 3, 4, yeah. So all those, and he used a lot of examples to explain. And this strategy is one of them in this book. Okay, this golden rule, this strategy is one of the, several strategies in that book. Okay, yeah. All right, so here, let's apply it. Yeah. How to choose a simpler case? Yeah, here. Because the general case, we feel, using our background knowledge, we feel a little hard to solve. Yeah. Now we want to simplify it. Our first try, we only want to solve the simplest possible case. Yeah. So for what C is the simplest? If C is 100, do you think it's simplest? If C equals 3.5, do you think it's simplest? Yeah. The simplest, C equals 1. Because when C equals 1, C is gone. Okay? No C. Yeah, you do not see that C explicitly. Yeah. So you get a simplified version. This time you only need to solve dy over dt equals y. This simpler equation. Okay? Yeah. To solve this one, yeah, our first step, solving this differential equation. Y prime, yeah. This dy over dt, just another way to represent y prime, right? Yeah. So same thing as y prime. So y prime equals y. Now we need to use our background knowledge. At this point, we need to search our background knowledge. All right. So here, we use our basic calculus knowledge. Yeah. So you should have it. Everyone should have it before you come to this class. All right? Yeah. But first, before we do the search, we need to interpret this equation first. Interpret. What's the meaning here? Yeah? We need to interpret. Then we can do the search. First, we need to understand this equation. Then we do the search. To understand, that is, given a function, we need to find a special function. That function has this property. What's that property? Its derivative equals itself. That's the property, right? Yeah. When you take the derivative, no change, you get the same function. How about that? That's the interpretation. Okay? Yeah? So, what function has the property that its derivative equals itself? That's our interpretation. Now you can do the search. Search your, knowledge base in your mind. What function has this property? Its derivative equals itself. Yes. Exponential function. E function. E. Okay? E to the t. Or e to the x. Yeah. Depends on what variable do you use. Here, t, e to the t. Okay? Yeah. So you find it. Yeah? You find the solution. If you know this property, this special function, e to the t, its derivative equals itself, then you can find it. Yeah. You can find it. Yeah. 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 Some students may not be familiar with the derivatives, some students may not be quite familiar with the derivatives of the functions. So then it's hard. Then it's hard. So for this step, you can see, if you do not know this fact, we treat this as a fact, right? If you do not know this fact, by logic, how can you find it by logic? Here we need to use this fact. So we know when we solve a problem, sometimes we need to use the logical reasoning, sometimes we need to use the facts, a lot of basic facts, right? Important. But here you can see, here we rely on that fact, if you know that fact. If you do not know by logic, you cannot find it, right? How can you, based on the logic reasoning, how can you get it? So here you cannot get it by logical reasoning. You need to know that fact. So that's the important. All right. So we can write, because we verify y prime of t equals e to the t. Same function. So we find a special solution. When you find this one, it's a special solution. Okay? It may not be the general solution. It's a special, only one special example. But it may not be the general solution. Okay? All right, so let's continue. So here you can see we have, good progress. So we find a special solution for the simplified equation. We simplify it. So then we find a special solution. All right, so let's continue. We want to complete the remaining part of the solution. Our goal, we want to find solution for this case. We go back to the original equation. Our goal, it's not we want to solve a simplified version. We want to solve original equation. All right, but we already have good progress. Solution for this one. Starting point. Now we want to modify this special solution. Try to move gradually to get a solution of the original equation. Okay, all right. So here, because if that's a special solution, we want to consider more general solution. Okay, more general than that special. Special solution is good, but we want to do more. Okay, so we want to have a more general solution. If we multiply a constant, a is a constant. A constant, we multiply it before that e function. It is still a solution, right? Think about it. The derivative of this function, the same as this function. Because that a constant, when you take derivative, you just take it out. Okay? When you take a derivative operation, this constant number can be extracted out of the derivative, right? Based on the, simple property, derivative. So here I'm talking about a property we can use. All right. Let's say a y derivative. Okay? But a is a constant number. Equals a constant. You can take it out, extract it out. Then y prime. Okay? So in that way, you can see this constant multiple of e function, it is satisfy this simplified version differential equation. Yep, still true, right? Then, because this A, we can change, right? A could be 1, could be 2, could be -1, even A is negative, it's still true, right? Yeah, any constant. Yeah. Even A equals 0, it's true, right? Even A equals 0, it's true. Yeah. Any constant we can put there, okay? Yeah. So then, that flexibility, so A value, flexibility, give us some freedom when we want to determine certain condition. We have freedom. Okay? So this more general solution give us one freedom in this A coefficient. And this special solution, there is no freedom we can use. Okay? Yeah. If you have more freedom, then you have more flexibility, you can adjust to the given input data. Okay? So more freedom is better. Okay? You have more room to find a solution. If you have no freedom, then much harder to find a solution, right? If the given data does not fit, then you cannot do anything. But if you have some freedom, yeah, so you can adjust, you can take advantage of your freedom to make adjustment, and hopefully you can find that solution. So freedom is a good thing here. Yeah. All right. So with more flexibility and freedom here, yeah. All right, yeah. So but here, this A, you can see because it is this version still satisfies this equation, not original equation. Now we want to find the solution for the original equation. Okay, all right. So now, this time, that C, we want to put in this position. Okay, in the exponent. Yeah. Yeah. Here, this place. Yeah. Here. Why I spend so much time here? I do not give you the solution directly because I want to show you how to do the problem solving. You need to do a lot of thinking work, logical reasoning thinking work. Okay, yeah, so that's the reason. So we spend more time here. All right, mainly teach you the problem solving strategies, techniques, and thinking. Yeah. All right, so here, to put a C in this position, you need to use your imagination. Yeah. In problem solving, you can see that you need to have, for problem solvers, so we are problem solvers, okay? So in order to be a good problem solver, yeah, so you need to have many skills, okay? Yeah. A lot of capabilities you can do, yeah. So here you need to use your imagination, okay? Yeah. So the imagination is, that C, you want to put in different places, not before this function as a coefficient. Yeah. In the position of exponent. Yeah. Put in that position. Then by the chain rule, derivative chain rule, right? By the derivative chain rule, when you take the derivative, then you multiply that C to this E function. So you have an extra C constant before the original function. That's what we need. After you take the derivative, you have an extra C in front of the original function. Yep. That's what we need. Here, by the chain rule, you get it. Right? By the chain rule, you get it. Okay. Yeah. So now you can see we want to get a general solution because this is still a special solution, right? Special. So now let's want for the general solution, we multiply another constant a in front of that e to the ct function. So that's the general solution for the original equation. Yeah, this original equation. Yeah. Finally, we get it. Okay? That a, yeah, a undetermined, right? So that a at this point, because c is given, so we do not treat c as undetermined. C is given, okay? But this a is undetermined, okay? Yeah. So that undetermined factor a, we can use it later on, because we want to fit this function for some initial condition. No? Because our question, there is some initial condition. We need to fit it. So we use this a freedom. We can make it satisfy the certain initial condition. Okay? All right. So we keep it. So that a factor is useful. We keep it. All right. Now we can, after this, now we can go back to our original problem to find the final solution. Yeah. So this is our decay model. By physical law, we get this equation. All right. By physical law. All right. And the k constant is given. K constant is given. Okay? All right. Our goal, we want to find the half-life of the radium in years. That's our goal. Yeah. All right. Then, initial condition, yeah, because initial amount of radium, 1 gram. Okay? So y of 0 equals 1. 1 gram, the unit gram. Yeah. All right. So let's continue. Yeah. Yeah, let's plug in. Yeah, because we have this form. Yeah, general function. Yeah, so we start from this general function here, but we need to plug in the initial condition. Okay. Yeah. All right. So plug in the initial condition. When t equals 0, its value is 1. Let's plug in t equals 0. Yeah. Yeah, because here we verify. This step is the verification. So we want to see if this function is really the solution of this original. So that's the verification. Okay? Yeah, verification. All right. Then we want to connect to our current equation. Yeah. All right. C equals negative k this time. Okay. C equals negative k. Then we need to write y function as a times e to the negative k times t. Yeah. All right. So we move closer and closer to the destination of the current problem. Okay. Yeah. All right. Then we apply the initial condition. Now you can plug in. Okay. When t equals 0, let's plug in both sides. Yeah. The left-hand side, yeah, right-hand side, yeah. Y of 0 given, it's 1, but the right-hand side, you plug in t0, e part is gone. It's 1. E to the 0, it's 1. So you have a left. That means a equals 1. Okay? So your freedom factor a, now we use it because we can adapt it to the given initial condition. Okay? If the initial condition, initial radium amount is 2.5, then your a becomes 2.5, right? So you can change your a to match the given initial condition. That's a good thing, right? Yeah. If you don't have the flexibility, then you get stuck. Okay? Yeah. All right. Yeah. Now, let's get a final solution. This is the final solution because a equals 1. Okay? Yeah. We replace a by 1. That's the final solution solution for the function, yeah, for the amount of radium function. This solution for what? Final solution. Solution for what? Solution for amount of radium. Yeah. We know the meaning of Y is amount of radium, right? So you need to keep in mind the amount, yeah, all right, amount of radium. All right? Yeah. All right. But our goal, half-life. Our goal is we want to find a half-life. Yeah. So this is not our goal. Okay? The amount of radium. All right. Calculate the half-life. Yeah. By the definition, yeah. So I covered it. By the definition, the half-life, we need to determine a special point, T1. Okay? Yeah, here we use this, yeah, because half-life appears at certain time. Half-life appears at certain time. So we want to determine that time. That time we call it T1. Okay? T1 corresponds to the half-life, 1/2 of the amount. Okay? All right. Yeah. So why we plug in T1, half, the meaning half-life, that half, 1/2 of the original amount. Yeah. All right? So then, this equation, e to the negative k times T1. So we need to solve this equation for T1. Okay? Yeah. That equation, only one variable T1, but we need to solve it. Yeah. So by our algebra knowledge, we need to solve it. Okay, all right? To solve for T1, yeah, take natural log of both sides. Take a natural log of both sides. So it's gone, right? Natural log E is gone. Okay? Yeah. So after simplification, you have T1 equals log, natural log of 2 over K. Can you see that? Yeah, here, I hope you can see it. Because when you take natural log, so here, directly, natural log of 0.5 equals negative k T1. Right? Yeah. The first time you take a natural log. Left-hand side, natural log of 0.5. Right-hand side, negative kt T1. All right. What is natural log of 0.5? Natural log of 0.5, ln, 0. Can we write 1 over 2? 1/2? 1 over 2. Okay? 1 over 2. Can we write it natural log 2 to the negative first? 2 to the negative first. All right? Then there is a property of log property that negative 1 can be bring to the front. Negative n of 2. Okay? All right. So that means here it equals negative ln of 2. This negative and a negative cancel out, right? Both sides you have negative. Left-hand side, right-hand side, negative. Cancel out. Yeah. Then T1 equals ln of 2 over k. Okay? Yeah. So here, review some simple algebra. Yeah. Yeah, because based on my experience last year, some students not quite familiar with even, this kind of simple algebra. Yeah. Especially this place, yeah, that place, okay, yeah, negative, yeah, exponent number, yeah, log, yeah. All right. So then, after you do that calculation, the last step. Oh, Well, we spend so much time. Yeah. So you find the answer, last step. Yeah. But that one, yeah, that one, because this time you need to pay attention to what's the unit. What's the unit? Because K, the unit of K, 1/2. Now you take a reciprocal, another reciprocal, 1/2 already, so another reciprocal, it becomes second. Okay? So the T1 time, this many seconds, that many seconds. But we need to convert it to, yeah, because that's the second. Yeah, we need to convert it to the number of years. The years, approximately 1,570. Yeah. In a previous slide, we gave an approximate number of the half-life, 1,600. Yeah. So here, more accurate, yeah, 1,570. Yeah, close to 1,600. Yeah. All right. So we complete that solution. Okay? Yeah. All right. Any question? Yeah. Yeah. All right. Yeah. So let's take a 10-minute break.